You can maybe help, somebody else can help you fill them in, or you can listen to the, yeah. So, solar energy, anybody? Okay. And so we actually are going to dive into the energy that the sun is sending us. You know, it's sending us heat, it's sending us energies that, quite frankly, thank goodness to the Earth's atmosphere for blocking some of those harmful energies that the sun's sending us. Okay, but I believe in solar energy. So this is an array of panels that's all feeding energy up to one point up there. I know it doesn't come without its problems, but...
Don't stand at that point.
So a lot of energy comes from the sun. We're going to be talking about latitude. You know, when you go into real estate, it's location, 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 right? Okay, so if I were to ask you where is it generally warm, you would say... Near the equator. You know, go with what you know. And where is it generally cold?
Near either of the poles.
Near either of the poles, yeah. So we're going to kind of talk about that, obviously. But what you just described, the equator or the poles, actually, that is changes in latitude. And we're going to have to talk about latitude. I'm going to kind of remind you if you don't know what latitude is. So one of the things you probably already know is that in the middle of December at noon, the sun's hanging pretty low, isn't it, at noon? You know, noon's the highest the sun's ever going to get for that day, okay? Well, we're past the middle of December. Of course, the sweet time is what we call December 21st or 22nd. It's called the solstice, the winter solstice. Once you get past the winter solstice, at noon, the sun is getting higher and higher in the sky. So, actually, though, how do I say this? Okay, the sun is this high in the sky at the winter solstice. Dang, it's low. But honestly, if you were to go, we are about 40 latitude, 40 degrees north of the equator. That makes us 40 north latitude. That's our latitude. If we were to approach the, if we were to approach the pole, actually the sun would be even lower and lower in the sky. So what your author did was to actually pick a latitude and find a happy time. Notice the date. What's significant about that date? Summer solstice, exactly. How high is the sun at the summer solstice at noon? The highest it's gonna be, yeah. To get it straight overhead, we would have to go to a latitude of 23.5 degrees. So here's zero. The equator is 0. Okay. Right here, I don't know if you guys can see this dotted dot. Okay, but that's the sweet point. That's one of a couple of sweet points on the globe. Okay, and there at noon on the summer solstice, it's right overhead. Okay. Yes, Tropic of Cancer, actually. Mm-hmm. So for us, the highest we get is 73.5 degrees. I'm going to go with that. Okay, 73.5 degrees. Do you see where my hands are open? This is the horizon, okay, and this is where the sun is. Actually, angle is so much of a player, and I'm going to try to convince you of that, okay? At the winter solstice, this is the noon. Is it very warm? No, it's cold. Okay, summer solstice. Okay, so it's about angle. Angle has consequences. Whenever the sun is high, it has a large angle. Whenever the sun is low, it has a small angle. So kind of remember that. So here's another one. Again, 40 degrees north latitude. 6 months later, and this is what I first described. There's these cool, I can't remember what they're called, but have you ever seen kind of like a figure 8 of the sun? Okay, and that's kind of where the sun is at throughout the year. And this is actually during one of the equinoxes. When are our equinoxes? What months are they? When does spring begin? March, right, very good. And when's the other one? September, yeah. In March and September, and I have a slide to but I want to introduce the idea. March and September would be our spring and fall, respectively. And those are sweet times in the Earth's travel around the sun, too. And we're running about, the noontime sun is about 50 degrees. Okay, so that's at our latitude. It's kind of fun. Because the little dabbling I do with astronomy, the whole comet thing, you need to know what your latitude is in order to kind of find your way around the sky. So this is a slide that you don't have, but I went ahead and I have some printouts. Oh, that reminds me, I have 2 printouts. Let's talk about this one first. Okay. So what latitude are we at?
You said about
40 is.
About 40, exactly. Exactly.
I think it's like 42.
Yeah, I wrote it down, but I've seen different numbers. It probably
42 by 107 or something like that.
Yeah, and I'm a little, in Burlington, a little north of y'all from Keokuk, so. I live in Burlington, yeah. There's a couple more to pass down. But lines of latitude are drawn here. Okay. Make sure we're all on the same page.
And we all have the same page.
I hope so. So, if you say what latitude you are, you always have to say relative to the equator, which is 0 latitude. Yep. You have to say if you're north or you're south. Of course, that kind of splits us up into the northern hemisphere and the southern hemisphere, right? Okay. So we are about here if you kind of go along like that. So the other lines that are drawn are longitudes. And to me, longitudes are kind of, I think of time zones. How many time zones do we have here in the United States? What's the fifth one?
Is it Alaska?
I think Alaska has its own time zone. Okay.
Is that right?
In the contiguous US, we have 4.
Yeah.
Yeah. So this is how this works, and I think this is going to work for you. Let me see. Let me go ahead and I'll put that over there. Okay, so the sun is going to be where you guys are. Okay, you'll just have to kind of, you okay, Joe, with that? Okay, the sun's going to be over there. Who gets the sun first? Wait, first off, let me find, okay, here we go. What time zone is this? Eastern. What time zone is this? Central time zone? Mountain. Very good. Time zone? Pacific. Those used to be more important than they are now. They used to be really important if you want to watch a TV show. Now I'm like, it's cable. They just kind of just throw it out there. Very good. So we have 4 time zones. So who gets daylight first?
East Coast.
East Coast. Go to the sun counterclockwise.
Before the sun, go the other way.
No. Clockwise. Counterclockwise. Oh, okay.
What was that?
Well, I think I want to do this. Okay, I'm cool. I'm eventually going to move this the other direction. But I put this here because you guys are the sun. You guys are the sun. So do you guys buy this, that this is daytime? And what's this over here? Nighttime, exactly. The moon may or may not be over here because the moon kind of does its own thing. But this is nighttime and that's daytime. Okay, so here we go. This is North America. Okay, here's the United States. So who sees the sun first? Yeah, East Coast. And then what time zone? Us. And then what time zone? Mountain gets dawn. And then Pacific, exactly. Okay, so, and then over here, this kind of transition, this would be going to dusk and nighttime, right? So who gets nighttime first? East Coast. Who gets nighttime next? Central, then Mountain, then Pacific, exactly. So this actually is a little bit of a player in how the global weather patterns are. Okay, so we do a lot with digital clocks these days, but if you think of a clock with the noon, 1, 2, 3, 4, what direction am I going? Clockwise or counterclockwise?
No, counterclockwise.
I am going counterclockwise, exactly. And most of the planets actually, when they spin on their axis, like the Earth is doing this once every 24 hours, right? They go counterclockwise, most of them. One of the things that all planets in our solar, did you hear that they think they found 2 more planets? Oh my gosh.
Drop 1, found 2.
Yeah, I was like, because my husband's like, they think they're big enough, but they cleared their orbit, right? But to kind of put in perspective how far out those planets would be, 30 AUs, 30 astronomical units, is where Neptune is, and they're looking at 200 and 250 astronomical units. You're like, really? Okay, counterclockwise. So the other thing, and I'm going to try to do it right here when I orbit the sun.
What does the sun look like on one of those plus surfaces?
I don't know. Be strange. The other thing is we are orbiting the sun, and what works well for this lecture is this is the sun, okay? So again, it's counterclockwise, okay? So it's like walking and chewing gum at the same time, okay? But if you were to look down at me, I am with the Earth. I'm going around the Earth counterclockwise, like that. Yes. Okay, so longitudes, lines of longitudes kind of remind me of time zones. Okay, the other thing that I want to make sure I give you is I went ahead and made a sheet that I posted on Twitter, so some of you may have already seen it. But if you're wanting to do your weather log, this is, and I know I won't lie, but I killed a tree for you guys. This is if you're doing your weather log, directions, kind of succinct directions on how you can fill out your weather log, going to two different sites. I wanted one site, but.
Killed a tree for.
So it's a thought. Oh, I need one more down there. The first page is everything. The first side that says 32, that's everything except for the record high and low. And then the back page takes you to Weather Underground. I kind of wanted to avoid Weather Underground for some reason. It sounds so dark, but I did on the back side say just go to Weather Underground, and I showed you how to go ahead and get your
Just call it Wonderground.
Wonderground. I know.
Doesn't sound as bad.
I'll say, I was gonna say, Kentucky was the same thing, that's all it's like.
Yeah. Well, I checked in telecast, and actually, from what I saw, it didn't give me tendency unless I went searching for kind of historical pressures. I wanted tendency, and actually Weather Underground gives you everything. If you look at kind of the without the 32, this one over here, it gives you everything except tendency again, Weather Underground. So I'm like, can you not do this, please? Okay, so that's that. Let me know if you have any questions. So, oops, I went backwards, didn't I? Okay, so what's the difference here?
Well, you're on the top of the pivot point, so the change in
What do you mean
the
by,
angle is
I
not
think
gonna
you
be-
are. What do you mean by the top of the pivot point? Is this what you mean?
Yes.
Okay, this is what's different about the other figures that we looked at. So 80 degrees, let's pick on north. We're northern hemisphere people. 80 degrees north latitude. Where is that? Okay, we are here-ish. Yeah, it is going up this way. 80 degrees. And what's that?
You're the pole.
Yeah, you're right near the pole. Actually, the sheet I gave you has 80 degrees on it, okay? So the thing about 80 degrees is you have passed, and we're going to be talking more about that actually today. If you go from 40 towards the poles to 80, you have passed another sweet mark called, and I have a sheet for this, what's the 66.5 degrees north latitude? What's the name for it? Tropic. Nope. That's the 23.5 degrees. It's not a tropic, it's the Arctic Circle. The Arctic Circle is another important latitude. I have a slide coming up, but then that's 66.5 degrees, thank you. North latitude, there's an analogous latitude line in the southern hemisphere called the Antarctic Circle. If kind of people have seen that, is it 9 Below with that dogs? I love that movie. 8 Below. It's so good. Little tearjerker, but drive safely. Harry. Okay, so this is above that important point. And I'm going to try to convince you of this, but honestly, as the Earth spins and daytime comes for up here near Santa Claus, right? Okay, at this time of the year, what's this time of the year? Is it summer or winter? It is summer. That's the solstice. Well, as the Earth spins, it's daytime the sun's up 24 hours. That's kind of why you see the sun kind of going and dipping down, but not setting. And I mentioned that because it would be hard to sleep. That's the case if you are north of that, the Arctic Circle, if you're north of 66.5 degrees. There's like a vampire movie out there where basically they kind of migrate. Okay, yeah. So if it's summer in the northern hemisphere, what season is it in the southern hemisphere? Winter. It is opposite, exactly. And I'm going to try to convince you of that. Yep.
And then they have night.
And then they have night. So I said it's all about angle. Okay, so I stood here and we kind of talked about the sun's low on the horizon at noon when it's the winter solstice, and it's highest, okay, like 73 degrees at noon on the summer solstice, thank goodness. So with a large angle, and this is a large angle, this is a small angle, okay. With a large angle, we have two specific consequences. I'm going to talk about it. This one talks about what we call beam spreading. Okay, what I mean by beam spreading is basically you have a shaft of light, and if it's a 90-degree angle, like the first slide says, 1 unit of light spreads on 1 unit of area. Yeah. If you start to get a slant with the sun coming in, a smaller angle, that 1 unit of light, and in the next slide you can already see it, they use a flashlight to kind of show this, that 1 unit of light then spreads a larger area. Instead of 1 unit, it's 1.4 units. Okay, you get even a smaller angle, you have more what we call beam spreading. This is talking about beam spreading. I call it beam spreading because that's how I learned it. Does it look like beam spreading? That shaft of light, if it's a small angle with the horizon, has to go for a larger area. Exactly. So here's one for you. Let's switch, don't do the whole 6 months apart. Let's not go with summer solstice or the winter solstice and the summer solstice. Let's just go with one day. Okay. So the sun appears to rise in the east and it appears to set in the west, exactly. So in the morning, when the sun rises, do we have a small or a big angle? Small angle. Throughout the day, the angle gets larger, okay? With this very small angle, and I'm going to go over here, this very small angle, with sun setting, right? Okay, we have a lot of beam spreading. Okay, the sun's shining, but that shaft of light hits the earth because of that angle, and basically, yes, exactly.
It loses its power.
That's why the front of my house
does.
doesn't get very warm. from
That's
the
why
morning
what?
sun. I only get morning sun on the front of my house.
Uh-huh.
And I get the afternoon sun. My kitchen gets so hot because the afternoon sun is a lot higher and it comes through. My
It's
kitchen.
interesting
So
how
hot.
your house is situated is usually very much on purpose.
Right.
You know, to kind of optimize the sun's energy. So this is showing you beam spreading. So can you see where the largest angle would be 90? Okay, we have the smallest area of the shaft of light. Over here, we go ahead and put it at a slant. Instead of 90, it's 45. And notice the area is larger. Same shaft of light, hitting a larger area. Okay, it just is. Okay. It's all about angle, or a lot of it's about angle. So this is a good figure from your textbook, okay? It shows one particular scenario. Now, in order for this to start to make sense, I need to talk about the Earth's tilted axis of rotation. So I went ahead and I have a ruler to yardstick to actually be the thing that the Earth spins on. Okay? Imaginary, that's right. So long ago, about 4.6 billion years ago, when kind of the planets were forming around the sun, okay, basically the Earth's axis was straight up and down. Remember what's the podium today?
It's the sun.
It's the sun, yep. Because physics would say when you're going to kind of coalesce and form, or accrete and form a planet, a series of planets, you have kind of material snowballing together to form our sun. Okay, what they're going to do is have, what kind of spin do we have? Counterclockwise. They're going to have counterclockwise spin and counterclockwise orbits. Okay, so there's a fair bit of evidence that says that planets that have axes that don't go straight up and down, like the Earth, they were basically hit early on by impactors.
Or in our case,
Comets,
another planet.
asteroids, small planetoids, yes. So that's actually what we think happened to the Earth, a significant single impact. Oops, sorry, I'm gonna go this way. Okay? I'm gonna
What was
go
that
this way on
planet called
purpose.
anyway?
I think I've heard it called Theia.
Thea, that's right.
So, here we go. Ever since it's been like this. But here's the cool thing, and this is important to seasons. It's almost like a dance, okay? So what you're gonna see is this, I'm gonna go, how long does it take for the Earth to complete one orbit? 365 and a quarter days-ish. How many months? 12 months, yeah. So I'm gonna show you what I do in 12 months, okay? But notice I'm trying to keep my tilt in the same direction. And I'm gonna show you a video that does the same thing. Okay, now it's still spinning once every 24 hours like that. So what if we take 12 months and divide it into quarters? So that gives you 3 months each quarter. So here we go. I'm gonna go a quarter. So actually, I'm gonna go ahead and let you in on what this looks like, or whatever. This actually, can you see where we're tilted away from the sun? This actually is December, the solstice, 21st, 22nd. 3 months after December, January, March, okay? This is March, okay? And actually, this configuration, when the Earth spins, it gives everybody's got, it's called an equinox for a reason. Everybody gets 12 hours equal, 12 hours daylight. 3 months later, so March, April, May, June. The summer solstice. And if you go with kind of, if you remember the month and then just slap on a 21st, 22nd, you're in good shape. So June 21st, 22nd, okay? Wow, does it look like the northern hemisphere is tilted? Okay. I'm gonna try to convince you it's not that it's closer to the sun that makes it warmer, it's actually angle. Okay. Okay, so June, July, August, September. Autumnal equinox, we're in fall. Another equinox, equal 12. Okay, and then we're over here. So let's pick on what, can you see where, does this look like the winter in the northern hemisphere?
Yeah.
Yep. And the caption reads December? Somewhere? See it? Maybe it is there.
It says winter solstice at the top. So.
Okay, thank you. You can put December 21st, 20th. Okay, so you see the tilt that we've been talking about. Now, that sheet I gave you, what is the name? Look on that sheet. What is the name for, in the southern hemisphere, the latitude that's 23 and a half degrees? Tropic of Capricorn. I remember this tropic because I think some of us get corns on our feet. Tropic of Capricorn, corns on your feet. So that's the one in the southern hemisphere. Tropic of Cancer, it's not written on here, is it? But it's the 23 and a half degrees north. So they are getting the most intense rays, okay? And the video I'm gonna show you says anywhere towards the poles from that angle's getting less, you have more beam spreading. Okay.
Why do they call it Tropic of Capricorn, Tropic of Cancer?
I don't know, those are
Celestial
good questions.
bodies.
I don't know. I don't know why they call a lot of things what they call things. I don't know.
Wasn't that related to the
Because science.
stars?
I was just gonna say the astrology.
The
of it.
astrology.
It was Capricorn and
Could be.
Cancer.
Yeah,
Could
they're
be.
Celestial bodies.
Yeah, of the things I tracked down and hasn't made my radar yet. But it's a good question.
Now, isn't the Earth axis shifting
Yeah.
by seconds? Or
The
minutes?
precession of the solstices, or yeah.
Does that affects the pattern of light?
That affects, it's hard to explain, but that has consequences to where the sun is when we experience our different times of the year, or different seasons. But one other thing I want to show you before I move on, there's something called beam depletion. There's beam spreading and beam depletion, and they both have to do with, excuse me if I don't spell right, so that means you don't have to spell right when you hand in your homework. Okay?
Right.
Yeah, Bob.
With angle also, with beam spreading comes beam depletion. And so here's the deal. The fuzzy blue stuff is the Earth's atmosphere. So the fuzzy blue stuff would be what? The troposphere, the stratosphere, the mesosphere, the thermosphere. It's the Earth's atmosphere, okay? And can you see where, if we look at this distance right here, okay, we have the biggest angle. Here we have a smaller angle. Here we have a smaller angle yet. And here we have the smallest angle. That green line that I've drawn is how much of the Earth's atmosphere that energy from the sun has to go through to get to us. Okay, beam depletion. So with the most exaggerated case up there, with the smallest angle, okay, that poor sunlight, it doesn't stand a chance. Not only is it spread when it hits the Earth, but it's depleted as it goes through the Earth's atmosphere. Beam depletion. Exactly. So that's what this figure is kind of telling you. Kind of in general, what this column is what the angle of the sun is making with the horizon. So 90-degree angle and getting less and less and less. And this column right here is telling you what is the consequence for that energy struggling to get through the Earth's atmosphere. So in other words, at what angle does basically the sun's energy have to go through twice as much of the Earth's atmosphere? At what angle?
30 degrees.
Yes, I buy that. Oops. 30 degrees. Does that make sense? Poor sun. But again, this doesn't just have to do with the latitude, kind of the time of year thing. This is actually morning, right? Noon and night. We have beam depletion. Okay, but we also kind of have it kind of as we kind of orbit the sun. Okay. So the thing about, in any science, you are faced with terms that you need to get under your belt. And you're probably already familiar with rotation, revolution. When I'm struggling with a new course, I hate it when the things start with the same letter, because I'm like, there's too many R's, right? Okay. But the other thing about me and learning is I don't memorize stuff. I just like to kind of start from scratch and kind of think holistically how they work together. So I have to concentrate sometimes. So revolution actually is the same thing as orbit. Okay, that's why I have orbit there. Okay, so the whole revolution thing is what you told me takes 365 and a quarter day. So just to kind of recap, we've talked about counterclockwise. Okay, you know, that would be 6 months from where I started. Okay, that would be like 9 months from where I started, and then I've done a whole year, keeping my tilt. Okay, so rotation is the Earth spinning on its axis. Okay, has it always been 24 hours to complete one rotation? Come on, you documentary people.
No.
No. Did it used to spin faster or slower? Faster. There are some awesome documentaries out there that just talk about the history of the Earth, you know, before there were
The
people.
moon used to be closer to
Yeah.
it.
Yeah, the moon is getting farther from us, right? The moon used to be a lot closer, it's getting
Used to
far
be
from
a
us.
lot.
Mm-hmm.
Which,
And the Earth used to spin a lot faster.
does that change, like our, the tides coming in, things like that, are they different?
The tides would have settled down into what they are now from what they used to be. The tides would have been even more exaggerated when the distance was
Less and less as
closer.
it gets.
Mm-hmm. So, R,
There was a time that
revolution and
the
rotation.
apex predators at a time feed off the tide lines.
Yeah. So, one other thing I want you to kind of be aware of is with regard to the Earth and Sun system is this. It's kind of cool. And it kind of goes back to way back when basically instead of the sun and planets, we just basically had a blob called the solar nebula that turned into the sun and the planets. But it was like one big frisbee and took a lot of time, but basically it ended up as kind of one big frisbee. That's to say that if this is the Earth, okay, what's the planet after the Earth?
Or
Venus is here, Mercury's
the
there,
other side.
starts with letter M.
Mars.
Mars, that's right, okay.
The
So
guy
Mars,
who-
Earth, Mercury, sorry, Mars, Earth, Venus, and Mercury, they all kind of do like a record player sort of thing. And actually we call that the plane of the ecliptic, okay? That's the plane of the ecliptic. And one of the things that a long time ago, like the 1700s, they figured out, and it took a group of scientists, is basically if you were to take the ecliptic and kind of look at it, okay? So I've kind of taken it, I've tilted it up. That sun is not in the center of where the planets orbit, okay? It's kind of off-center, but it's in a cool geometric shape. Instead of being a circle, the orbits of all the planets are ellipses. I know. But where that brings us to is kind of the off-centeredness of the sun. The sun lies at a cool spot, an ellipse called a focus. So I know, and it's the same focus for all the planets. Yeah, foci. Focus, I think foci is plural. So. But that's all, the reason I said that is, honestly, there are times when the Earth is closer to, since the sun is offset, there are times when we're closer. But here we go. So, what did we say, what time of year is this?
Winter. Oh, no, that's spring.
Summer.
Summer.
Yes, I'm trying to, this is summer. This is summer, Autumn. Yeah, this is summer, yep,
Right.
okay. So actually, July, what do I have? July 4th, okay, the sun is as far away from the Earth as it's going to be. This is backwards from our which you just have to bear with.
Yeah.
Okay. So we call that, what term do we call that? Aphelion, very good. This is aphelion, okay? And over here in December, in January 4th, okay, we are a little bit closer, perihelion. So here's the little conundrum, January 4th, okay, we've just passed the December 20th, 21st, what season is this?
Winter.
It is winter, and yet we're closer.
Huh.
Like, dude, how does that work? And this is where students have asked us an assortment of questions, one being, what? Okay, but I know it looks like a significant difference. This 147 million miles versus 152 million
Taking
miles.
into perspective how far away we actually are though.
And actually, as an object, kind of, yeah, what you're saying, as an object like the sun gets farther away from the object it's beaming on, there's this thing called the inverse square law, which just says basically the energy gets diluted very quickly. Okay, and that's kind of what we have going on here. So this distance doesn't make much of a difference. And a lot of times students will say, does that make their summers more intense and their winters, okay, yeah, more intense, okay, because they actually are coinciding. If this is our summer, you know, at aphelion, okay, this is their winter.
Theoretically, maybe, possibly, but
Yeah.
But like you
nowhere
said,
near
it's
enough
not-
to be actually measured.
I think the numbers,
far away
the
it
numbers
is.
crunch that no. You know what does make a difference? Oh my gosh. And this isn't in this chapter. But which hemisphere, have you ever thought about it? Which hemisphere has more blue? How many
Southern
people
is in
think
ocean.
it's the southern hemisphere?
Yeah.
The southern hemisphere has more ocean. And that's the bigger player with the southern hemisphere. They got more poisonous stuff too, but that's unrelated probably. But they have more oceans. Okay. And what oceans are great at doing is basically maintaining their temperature. If you've ever had a swimming pool and you're like, you fill it up, it takes a long time for it to heat up. But once it's warm, it takes a long time for it to cool back down again. So that's what the oceans are. They're kind of ooh, I'll just keep what temperature I got. So actually, that's more of a player between the
Doesn't that
hemispheres.
depend on how large the ocean is? Like, I've been in the Atlantic and the
It's
Pacific
also interesting
at
to
about
do
the same time of year.
Yeah, size would make a difference, yeah. But the thing that makes a difference between, the thing that makes a difference between the Atlantic and the Pacific is the prevailing ocean currents, yeah. So it's around a high going clockwise, so basically we have cold water coming down here and we have warm water coming up there.
Yeah, the Pacific was really cold. when I was
Cold,
in it.
warm.
Really cold.
Yeah, interesting. So I think this is kind of a rehash slide. One thing I didn't mention is, this talks about Polaris. So what's the significance of Polaris? When I do this dance, It's a Polaris is the name of the star. It's the North Star, exactly. When I do this dance, one of the things that and actually you can observe this in a night, in a given night. It'll stay, Polaris is the star that won't kind of rise in the east and set in the west. Everything kind of goes counterclockwise around Polaris, okay? So.
But it does change some perspective.
Yeah, there is some of that. And actually, through the course of, I think it's 240,000 years, our North Star actually would go through Vega. I don't know if you're familiar, I love Vega.
Mm-hmm.
So actually the North Star would change. But right now, it's Polaris-ish. Okay, so this is the slide I handed out. And a lot of times when I'm looking for kind of the test that you're going to take several weeks from now, it's have assortment of questions, but this is like one of the kind of the straightforward sort of questions that I can ask you, is kind of these important lines of latitude. And we've already talked about why this line of latitude is important, the Tropic of Capricorn. Remember we saw when it's...
Most intense light.
Yeah, the most intense light at the winter solstice for us. And the most intense light for the summer solstice for us actually is the Tropic of Cancer. So those are both kind of analogous lines of latitude in the southern and the northern hemisphere respectively. I'm going to try to convince you of what's so special about 66.5 degrees in both hemispheres. Vampires? No. But really, that actually is an important line too. So know those, okay? The circles and the tropics.
Vampires are beat by one PO boy.
So this is where I want to go ahead and play you this video. I think she does a great job. I'll go ahead and show you. So see the Earth, how is the Earth orbiting? You kind of see the arrows. What direction? Counterclockwise, and it's spinning counterclockwise. Okay? And it's broken into quarters, so those quarters are 3 months apart, right? So that's one of the other things I want you to be familiar with. Notice we have the 2 equinoxes here and the 2 solstices here, 6 months apart. Okay? Feel free to use your fingers to count 3 months. If you go ahead and say the 21st, 22nd for everything, I'm cool with that, even though this says that the fall equinox is 22nd, 23rd. So I want to play this video for you. I think she does a good job.